Okay. Now we back to our linear time invariant systems. We know that what's the meaning of this linear and time invariance. What's the meaning of linear and what's the meaning of time invariance? We got the definition of this one. So keep in mind these two properties. When we consider a unit step, this one is the discrete time systems. In that case, this one is discrete time system. We apply the unit impulse. This is one only t equals 0. All the other time it's 0. This is applied to the system. Then the system response comes out like this one. This is just the impulse response of the system. If we have impulse response, then we can calculate all the other input if the system is a linear and time invariant. This is our basic assumptions. Discrete time signal can be expressed in this way. Xn is x minus 1 times delta n plus 1, like that way. You know that n is minus 1, then only this term is valid. All the other terms are goes to 0. If n is 1, only these terms are remain. All the other terms vanished out. So by taking sum of this one, we can express the sequence into the summation of weighted impulse. So weighted impulse. So any input sequence can be expressed by the weighted impulse sequence summations. We assume that the system is linear and time invariant. Due to the linearity, the scaling factor, you know what? This one is respond with the impulse response index n. Okay, then index n. So this is the index n. This is response variable, change of variable of the system. But k is just a scale factor. Okay. But we know that the linear system scale factor conserved to the output. If input is a scaled xk, when you know that delta function is scaled xk, then output also scaled by xk. Okay, and linearity also conserved the summation. Summation is also conserved, and impulse response we know the impulse response delta n, but the shift of impulse, it means that the n is shifted by k, but this system is time invariance. The meaning of time invariance, if input is a shifted version, then output just the shifted version. Then this becomes the output. Okay, I would like to rewrite the same things. Okay, here to figure out the output of a system, but the input is xn. Xn is applied here, but xn can be expressed in terms of weighted sum of impulse. Weighted sum of impulse. Okay, like this one. This input xn can be expressed weighted sum of impulse sequence. Okay, then system is linear and time invariant, and also we know that the impulse response. Then from here you can see that xk is a scale factor, summation is adding. We know that the linearity satisfies the additivity and scalability. So homogeneity and additivity satisfied, then output will be given like this way. Sum k x k times h something, like that. K will moving from minus infinity to the infinity. And we also have a time invariant property of the system. Then shifted version of the delta, just shifting the output will be given the correct output. So output also shifted by k. Yeah, this is the convolution operation. If a system is a linear and time invariant, any input can be expressed by the weighted sum of impulse sequence. Then we can apply additivity and scale factor based on the linearity and the time shift by use of time invariance of the system. So output system can be easily found by use of linearity and the time invariance, and the result is convolution. I talked about the meaning of a convolution in the previous lecture. It is past history weighted sum of past history. Okay, that is these equations. So here shows that how to decompose input sequence with the scaled impulse sequence. You can see the x0 scaled by delta n, x1 is x1 delta n minus 1. By summing up all this sequence, it gives the original input sequence. This means that any input can be decomposed sum of weighted impulse sequence. Okay, and this one, weighted impulse sequence applied to the linear time invariant system, then we can get the output response. That response follows the convolution operation. Okay. This is the same thing that I have to talk about. The calculation method are expressed here. Here is the input sequence, index 0, 1, 2, 3. It has a 0.3, 9, and 1, and minus 0.2. And the impulse response are shown here. H0 is 1, H1 is a 0.25, H2 is a 0.125, like decaying like that way. Then, due to the input sequence 0.3, 0.3 is the H0 is multiplied here, that is 0.3, and 1 quarter, 0.25 is scaled by 0.3, then it gives 0.075. 0.125 scaling of the of 0.3 are given like that way. It means that the input at n equals 0 spread out this way. You know that impulse has 3 time memory, so it has 3 terms that exist here. Second, if 0.9 is applied at index 1, so this contribution starting from this index 1 and goes down 3 terms, scaled by the hn. And similarly, index n equals 2, the input 1 is applied, that this one contributing from this time to the up to here. And lastly, index 3 applied minus 0.2, that affecting in these patterns. You know that this one is just scaled this impulse and spread out this memory effect. So this one spreading in that way, but 0.3 spreading in that way. By summing the old contribution of that, then we can get the convolutional output like these patterns. Okay, so this shows that how to calculate the convolutional operation.